I'm going to talk about concurrency model, actor model, and CSP between Elixir and Clojure, using Elixir and Clojure as examples, but really about how BEAM and JVM also under the hood differs and works. So first, a bit about myself. I work for remote as an Elixir developer. I live in Berlin. So this is my website and my Twitter, which I don't use very often anyways. And the obligatory plug for, because the company sponsored my trip, we're hiring Elixir developers. If you're interested, working remote, take a look, maybe after the talk, not now. Okay, so about this talk. I have to confess, I'm not an expert in any of the topics here. It's just something that intrigued me, and I wanted to do a research on this topic, and I submitted a proposal. So I'm here just to share my findings, my learnings with you, learning together. I guess there might be experts in Clojure in the audience that know much more than I do. I may make some mistakes in the talk. If I do, then just point it out. Okay, so I'm actually going to do 2 dimensions of comparison, which is really ambitious. But I think I'm going to go short on some of the contents there. Focus on what's the difference between the JVM and the CSP part, because I guess the folks are more familiar with the BEAM and the actor model already. So this is an outline of what I'm going to do. First is the overview of comparison between BEAM and JVM, and then the actor model and CSP, and the walkthrough of how the actor model and processes work on the BEAM, and then how CSP and the implementation in Clojure called async works. And this part I'm definitely going to cover, which is the topologies and buffer types of the CSP, which also applies to Golang. And this, the second part is something specific to Clojure called async, which is somewhat specific to the nature of JVM. It actually has 2 variants of the routine, of the process you can do in CSP. If time permits, I will cover that. If time doesn't, then I will just briefly walk through it. And there's actually one final twist I learned at the end of my my journey. But if time permits, stay with me until the end. I can get there. Okay, so let me start with a BEAM, also Erlang runtime system. As we know, on the BEAM, every process has its own memory space on its own heap. So this is a diagram where we can see that it has its own heap, a stack, which is not shared with the other processes. Which a consequence of this is that you don't need to do a stop-the-world global garbage collection, because every process can have its own garbage collection. And this is very different to JVM, as we're going to see, because JVM will do a global garbage collection, and it will sometimes lead to a halt in all the threads. But this will never happen in the BEAM, because every process is very lightweight and the memory space is very small. It facilitates the actor model, which I'm going to go into later. And we have preemptive scheduling on BEAM and Erlang runtime system. What does it mean? So whenever you start ERL or IEX, you actually see this message printed out. And on top, you have the number of schedulers there, which corresponds to the number of CPU cores. What happens in each of the scheduler is each scheduler has a process queue, which has the number of processes which it runs. And the way it runs the processes is that once each process reaches a certain number of reductions, it will actually get interrupted and get put back into the queue. And another process will take its place. And this will always happen. I think the number I remember is 4,000 reductions. One reduction is about 1 function call. So what happens is, so this nature ensures we have consistent time sharing across all the processes, no matter how many processes there are. So you can run like hundreds of thousands of processes on the VM, and the performance is going to be really consistent. You can predict there's not going to be a process that hogs the CPU resource and then doesn't let other processes do their job. And yeah, as a result, it's not as powerful for very intensive processing tasks, because preemptive scheduling, of course, you have to yield to other processes, and also because of dynamic typing, which actually adds a lot of overhead at runtime compared to static typing. Usually you use NIFs, which are run on dirty schedulers, which is a DES thing you see on when you start the IEX or ERL. And also, you can also use POS to talk to other programs for such purposes. So JVM has a shared heap, so all threads that share memory with each other. And then this enables shared state concurrency, which means threads can modify other threads' memory state or reach into their memory state. But then stop-the-world garbage collection could result in halting all the threads because this is a bit not very clear, but the heap is shared by all the processes, and when the garbage collection happens, it will impact all the processes, all the threads. And the stack, it actually lives on the threads, which is different from the Elon processes. And the threads in JVM, they are just operating system threads. They rely on the OS scheduler, so it's not like BEAM, which has its own scheduler. It just relies on the operating system to do the scheduling. Therefore, threads are much heavier than the BEAM processes, of course. They have much more content. If you frequently block and unblock them, it's going to cause a lot of CPU operation because it's not optimized for that. And you also have to take care to not unexpectedly block other processes, other threads, if you're doing something on your thread. It might cause some deadlock, which is not a problem with BEAM. And of course, it's performant on heavy and sustained workload because it corresponds directly to the operating system threads. Okay, so now I'm going to compare the actor model and CSP. You're going to see how the virtual machine comparison is also relevant to this later. So the actor model was proposed by Hewitt in 1973, but Elon didn't actually look at the paper. I think we all know the story. They arrived independently at this model by themselves, which speaks to how good this model is, I guess, how naturally it makes sense it is. And then each process has a name. They will communicate with each other by message passing, but they will not share memory with each other. And one interesting property is that a process cannot refuse to receive messages. So in theory, you can always bombard a process with countless messages, and actually there's no limit on the amount of messages a process can receive. So you can theoretically overflow the whole VM until it crashes. And you have to define how to act on the messages you receive in the mailbox. By default, sending a message is non-blocking, and receiving a message is blocking. I'm going to illustrate in more detail what I mean. So this is just a very simple example, actually the example from the Elixir website. We have IEX, which is this process there. And we spawn another process, which we ask to send the message, hello, Pete, to the spawning process, which is IEX. And at this point in time, this message already arrived in the inbox, in the mailbox of the IEX process. Note that we haven't done anything about the receiving. So this message is already there. And now we start the receive block, which says if I see a message in this format, I will produce a binary got hello from Pete. So this is how we take the message out of the mailbox. What does it mean send is non-blocking but receive is blocking? So if I do some receive that doesn't match what I have in the inbox, it will just wait forever. It will not do anything because there's no message matching this unmatched atom arriving in the inbox. And of course, you can escape that by timeouts mechanism, but if you don't do it, it will wait forever. And also, see, you cannot refuse to receive the message because it's already there. Just as a side, of course, the OTP is much more than just the actor model. We have Gen server. That's why we don't really write receive manually. We have supervision, clustering, location transparency, tracing, etc. Those make up the whole package of the OTP, which is not so relevant here. But something to consider when you look at the language as a whole. So CSP and co-async. Another aside, so conventionally Clojure doesn't actually approach concurrency with this model, with this CSP. This is something Golang does at the core, but Clojure actually had a different model called software transactional memory, which relies heavily on the functional data structure, and it has 4 reference types for different scenarios, which I'm not going to go into details here, but it has a lot of nice properties, one of which is it kind of acts similar to a database transaction, where if you have multiple operations, they're going to be atomic. But fine, this is what happens comes originally with Clojure. And another disclaimer is that, of course, I think some people will say Clojure is not tied to JVM. Clojure is designed to run to be platform agnostic. It has Clojure script. Has also even on the BEAM, I think there's a Clojure realization. But today I'm going to focus on JVM in my talk. So core async. So Rich Hickley actually then released core async 6 years after the Clojure's initial release. That's quite a long time. And it's, of course, much inspired by Go's implementation of CSP. He felt it would be nice to add a additional toolset in the Clojure concurrency toolbox. We're going to also see a quote later on his explanation. So there are actually 2 types of CSP processes. But before that, maybe let me explain in more detail CSP, communicating sequential processes. It was originally proposed by Hall in 1978, but if you look at the original paper, so I actually went to read the original paper, it's a bit different than what Golang and the core async does. I'm not going to go into the details, but it evolved quite a lot over the years. Then in this model, what's different from the actor model is that the processes, they are anonymous while they talk to each other via channels. The channels are named, and channels can be persistent. But the processes, usually, if you, for example, spawn up a Go routine, after it finishes, it will be gone. It's not like the Elon actors, which will stay there forever. And it's blocking and synchronous by default. This is a very interesting distinction between that and the actor model. I'm going to illustrate with an example what that exactly means. There are variants such as buffer channels, which enable non-blocking behavior, which I'm also going to cover. You can also explicitly close the channel to further write. So this is different from the actors, where you cannot refuse messages. Well, a very interesting thing. I think this is true. I don't know if this is true or not, but this is what I think. In Golang and Clojure, you still facilitate working on shared memory. This is very different from actor model in BEAM and also Akka, which is the Java implementation of the actor model. So just here are some quotes. In Golang, you say you don't communicate by sharing memory, but you share memory by communicating. You still share the memory. And what happens is essentially you send the reference to a data structure from the writer to the reader, and the reader would then do further modifications on data structure. Theoretically, the writer can still modify it. There's nothing preventing it from doing so, but it's just a good practice not to do it. And also, this is from Rich Hickley's quote. He says this mechanism, when he introduced it, is oriented toward the flow aspects. It's actually not so oriented towards the concurrent use of state. All the nice STM things are still there, but it just offers an extra tool towards how you control the flow, how you talk to each, how you arrange the job in a queue-like manner. And so, of course, if you contrast that with something from the Akka documentation, you want to avoid the shared mutable states. This is very explicit in Akka, but you cannot really do that. So in Akka, you can actually send something across the wire, and the other side can modify it because you're on JVM, and there's no mechanism preventing that. This is different from the BEAM, where they're just isolated by default, so you cannot touch into the memory of the other process. Okay, so I'm going to do a walkthrough of a very simple case of core async in Clojure. This is one writer, one channel, one reader. So first we initialize a channel, which we name it C. So let's see this channel, we initialize it here. And then we spawn a thread. This actually will run on a JVM thread. It would put hello onto the channel, but note what happens after it puts. It waits for somebody to read it. If nobody comes to read it, it will just wait there forever. So I actually have another statement, print writer unblocked, but it will not happen at the moment because it's blocked. And now we spawn another thread, also run on JVM, like the JVM native thread. It will take this message, take whatever is in the channel. In this case, it's a hello message. I print it out. And now the channel is free again, so the writer knows it's unblocked. This is what synchronous means. So the two sides have to collaborate with each other. The writer has to wait for a reader to appear. And now we can get this message. So to recap, first it puts hello into the channel. It reads a hello from the channel, and then write unblocked happens. And then those two threads will no longer be there. And this can also be the other way around. So it doesn't have to be the writer that's blocked. You can also say, if I want to, as if I spawn the reader first and it tries to read on the channel, it will also be blocked because there's nothing on the channel. It's also waiting for a counterpart to appear to put something into the channel. So the synchronous goes both ways. So then the read unblocked will also not get printed until I actually run this part, which then I put something into the channel. And then we can see the read unblocked printed after the hello is read from the channel. You can close the channel. So it just, oh, I think there's a mistake there. Oh, no. Oh, yeah, it's fine. So I close the channel with a close statement here. Now I am not able to write into the channel anymore. But it's not a mistake because I'm trying to take it out of the channel, which is still possible. So in the second line, I put something to the channel and I close it, so it cannot be written to anymore. On the fourth line, I just take it out. It's just, and the channel still lives there. It's not dead. Okay, so some other more complex topologies compared to the simple one we just displayed. You can have multiple readers on the same channel, which means a message will only be taken once, but at most one reader. So a message can be taken, for example, by reader 2, and it will be gone. No other readers will get it. And I think in Golang, this will be delivered at random. And you can also have multiple writers and one reader. Because of the blocking property, if one reader, for example, one writer 2, put something onto the channel, but writer 1, writer 3 still wants to write to the channel, they will be blocked because the channel is full. You can also think of it that way. It doesn't allow any writing operation anymore. After somebody takes the message, then writer 1, writer 3, one of them can proceed, and the other one will still get blocked. You can also read from multiple channels. Basically wait on multiple channels. So whichever channel has a message in it first will get selected, and the reader will get a message from that channel. And in core async, it's called else. In Go, it's called select. And we also have, what I mentioned before, how do you achieve non-blocking semantics? One way to do it is to have buffer channel. So here, I have a buffer channel of size 10. Now, before the channel is full, I can actually put messages and just go ahead with other things. It will not be blocked. But Rich Hickley, he explicitly mentioned we shouldn't have unlimited buffer in core async. So he said he actually rejected many proposals, many merge requests trying to add this already. It's just not in what he likes. You can have a sliding or dropping buffer, which, for example, if you reach 10, it will just drop the first messages or the latest messages. Then you can put the messages into the channel forever. It still doesn't equate to unlimited mailbox we saw with the actor model on the BEAM. It's different. Okay, actually we still have time. That's great. So this thing I find quite interesting. In the example I did before, we used a thread, which actually spins up a JVM thread. But of course, because it uses OS thread, you're not supposed to spin up too many of them. This will actually slow things down a lot. And there's another variant in core async, which is called Go. I mean, the name is literally the same as a Golang Go. So what it does is it will, under the hood, it will do something like it will have a fixed size still thread pool, which is still JVM thread, but it's fixed size. It will not actually create new physical threads, and it will do some magic on the code. I think it's so. According to the explanation, it's similar to C#'s async that was 2013. So I think then ES6 also had async await after that, which is somewhat similar. And recall that in JavaScript there's only one thread. So also interesting property is that on the Clojure script you can only use the Go variant, but not use the thread variant if you want to use core async. This is similar to how async await works with JavaScript. And under the hood, it does some macro magic to transform the code into a state machine. So basically, if the code is blocking, it will be so-called parked, and it will be taken off the thread. And some other Go process would then go on the thread to keep being executed. This is, I don't think we need to go through the details of all the lines, but basically what it does is to, so here we see as we create the 1,000 channels, and we spin 1,000 Go processes to put a message into each channel. And this is actually very fast. It's done within a minute, within a second, which if you do with the thread, I think it will be a different outcome. Okay, so this is a surprise I got while I was researching this topic. I don't know how many people read this. So apparently, Java JVM is going to have virtual threads, and this proposal is pretty new. They will release it in September, probably in the 19th version of JDK. And in the proposal, they actually mentioned Go routine and Erlang processes explicitly. They're trying to emulate this kind of lightweight process because we need it. I think this is a consensus now. It doesn't have a built-in CSP because I guess in Java you shared memory. But it's still very interesting because it doesn't have a built-in CSP. It doesn't mean people cannot build it, leverage this to build a lot of libraries. And a lot of people are excited about this. I asked in the Clojure forum and the Clojure Slack what happens to Go async after this. People are not sure. There are many different opinions. They say they probably have to wait until this comes out. And especially, is there still a reason for the Go macro now that we have the virtual thread? Or are they going to prefer a different concurrency model? But one thing that's for sure is that Clojure has a backward compatibility with lower JDK versions, JVM versions. So they're not going to get rid of co-async in a flash. This thing is new, and I think adaptation will still take a few years. But what people say is that to lower the bar for competing libraries that implement different concurrency patterns. Like there are many libraries in Java because the ecosystem is huge. But I look into some of the implementations. For example, Quasar, it actually tries to implement some Erlang process like semantics, but it has to hack into the bytecode level to try to approximate lightweight threads. But with this proposal, it's going to be built into the JVM, which would be a completely different situation. So probably make it much easier to write the libraries. And also, if you look at the source code of the Go macro I just mentioned, if you go to co-async repo, it will be horrible. Yeah, so this is it, I think. Thank you.
Do we have time for one question, maybe? Or yes, I think. Any questions here on the Hova app? Oh, there's one question here.
So between these two paradigms, CSP and actor model, which one do you personally prefer and why?
I'm at code BEAM. The answer is obvious. So actually, Rich Hickley had a quote on why he doesn't prefer the actor model. But I don't really think that makes sense. He says CSP is more primitive than actor model. But I chatted with some friends as well. I think you can replicate the CSP semantics by having actor in the middle, and it will then relay the messages. But in the end, I think in the end of the day, those two things you can emulate the semantics of each other. You can do it, but it kind of encourages different things, and we build it together with you have to build it together with a runtime, right? So as we saw in Golang and JVM, they actually still have shared memory. So this is a very different encouraged use case than what we use actor model in Erlang for, which of course I find much more elegant.
Thanks.
No?
Are virtual threads also gonna share memory?
Sorry?
Are virtual threads in the JVM gonna have shared memory?
Yeah, I think what they want to achieve is just a more lightweight thing to do work, but it's not going to change so they're not even implementing CSP. They're not changing the shared memory model. But it will be much easier to spawn up like 10,000 workers. They will not clog the OS. You can still do things on those workers.
I think we have lunchtime now, right? Or do we have time for more? More? Well, if one more questions. Well, this is, I'm getting dizzy here. All right, I think that's it. Thank you.
Thank you.